Hello everyone. Welcome to the presentation Predicting Defect Resolution Time Using Cosine Similarity. Before we jump into the presentation topic, we would like to thank the conference chairs for giving us an opportunity to present our paper remotely. We request you to please hold on to your questions till the end of the presentation, as we will be available to take your questions through the Skype call. So, in this presentation, we will talk about some of the software project management challenges in industries which motivated us to perform this study. We will briefly discuss why it is important to predict defect resolution time and the approaches and methodologies used for prediction. We will also talk a bit about why we chose cosine similarity for making our predictions. And last but not the least, we will discuss the scalability and applicability of this study in different types of projects. Delivering an excellent quality of software on time is an implicit requirement for any company to ensure high customer satisfaction and to stay ahead of the competition. Often, projects suffer from missed deadlines due to open critical defects. This negatively impacts successful delivery of a product, resulting in loss of revenue and customer dissatisfaction. In this study, we have observed that predicting defect resolution time can alleviate the risk of missing targeted milestones. Through this study, we assist the product development teams to achieve targeted milestones by enabling quicker defect triage. Here we discuss the workflow used for days to resolve a defect prediction. Project teams use different issue management systems like Jira, Bugzilla, GitHub, etc. to maintain a log of all defects through the project's life cycle. Our defect data comes from total code base of about 5 million lines of code with various programming languages including C, C++, Java, etc. All these projects form significant components of mobile and IoT industries and have active contribution from more than 150 developers. These projects are evolving at a very fast rate, matching pace with the market needs. This paper roughly analyzes 2000 defects with defect contributions from the three projects as 62%, 21% and 17% respectively. Data is collected over a period of 15 months. For every defect in a project data, various fields such as defect ID, summary, comments, date of defect creation and resolution, status, priority of the defect, etc. is extracted by querying the database. Once data from the desired fields is available, next step is to process it to get rid of inconsistent data. Defects with missing key fields and resolution categories or ones labeled not a defect or invalid are safely ignored as they do not contribute to the analysis. For this study, we have used the defects in closed and resolved state and divided them into training and test datasets. We then calculate the DTR for defect in training set as difference of days between defect creation and resolution. Through this study, we provide two levels of prediction. One is preliminary prediction using naive-Bayes classifier and the other provides more granular prediction using linear regression techniques. We will discuss in details about computing cosine similarity of defects and each of these approaches in the upcoming slides. Here is a more closer look at our analysis. Cosine similarity, an extensively used measure for different text mining applications, determines similarity between two documents or texts. When a new defect is created, The reporter first populates the defect summary field describing the basic details of a defect. We use defect summaries to compute cosine similarity between every two defects in a project and Pareto similar issue using highest similarity score as the metric. This computation forms the basis for all three proposed approaches. We will explain how we compute the similarity score in the next slide. Next level is preliminary DTR prediction using naive Bayes classifier. We get to know whether a defect can be resolved quickly or not using this approach. This helps the project manager to effectively assign resources for resolving the defect that can take longer time to resolve. Finally, we use linear regression approach to accurately predict the days to resolve a defect. Cosine similarity in text analysis. Cosine similarity is an extensively used measure for different text mining applications. It determines the similarity between two documents or texts. To determine the similarity between two texts, an equivalent term frequency vector is first obtained. Following steps are performed to derive a term frequency vector. Given text is first converted to a lowercase. Punctuations from the text are removed. All common English words, that is stop words like a, the, of, etc. are removed. Frequency of each term from remaining text is then computed. All term frequencies taken together constitute a term frequency vector for any given text. Similarity between any two vectors is then computed as cosine of angle between them given by equation above. The value of cosine of angle indicates how similar or dissimilar the two texts are. Value of 1 shows that the two texts are exactly identical, whereas value of 0 shows that the texts are dissimilar and have no common terms. Output is always bounded between 0 and 1. In the example shown above, these are the sample defect summaries. We converted them first to lowercase, removed punctuations and stop words, and calculated the cosine similarity scores for each defect. A is similar to B with a score of 0.33. B is similar to A with a score of 0.33. For C, however, no similar defect is found due to no common words between either A or B. Naive Bayes classifier is one of the most popular supervised machine learning techniques and is extensively used for data mining applications. The motivation behind using naive Bayes classifier is to aid developers or project managers in identifying defects that can put a project at risk. We classify defects into two categories: defects having quick resolution and non-quick resolution based on independent features, subjective similarity, and defect priority. The values and parameters are as shown in the table. The values for subjective similarity are highest to lowest. Priority is P1 stopper, P2 high, P3 medium, and P4 low. And quick resolution is yes less than equal to 20 days and no greater than 20 days. Getting first-hand knowledge of defect resolution can motivate the defect reporter to take proactive actions to expedite resolution process and to keep project progress on track. We observe that defects with highest similarity scores, irrespective of their priorities, have quick resolution. Higher and high similarity scores defects with priorities P1 stopper, P2 high, P3 medium are also resolved within 20 days. Finally, defects with low and lowest similarity and priorities either P3 medium or P4 low do not have quick resolution. This model accurately yields a prediction of 80%, which is pretty good when we look at accuracy of text classification algorithms available today. This accuracy can be further increased by training the model continuously on more data. Linear regression. This diagram shows the workflow in predicting DTR using linear regression. It is important to first determine which factors contribute in predicting DTR. For example, the number of developers working on a defect can influence its resolution time, or if a defect is classified as a showstopper, there are greater chances of it getting resolved quicker. Also, if a similar defect was seen in the past, the developers might already know the fix and will resolve it quicker. Hence, we first identify the factors that contribute to DTR prediction using regression techniques. Several factors, including number of developers, components, severity, priority, similarity score, etc., can influence DTR prediction. We performed multivariate regression analysis on factors that are continuous in nature and logistic regression for categorical factors to find out which factors have most significant impact on DTR prediction. Once the factors were identified, the next step was to evaluate its outcome using different measures. The measures we considered are p-value, RSME, and nature of correlation. P-value determines how much significant role a given factor plays in prediction. RMSE determines a root mean squared error between observed and predicted values. Lower RMSE values are desirable for accurate prediction. The nature of correlation is either positive or negative. We observe that cosine similarities between defect summaries is the most significant factor for predicting DTR. As seen in the diagram, linear regression is performed on the training defect dataset with similarity score and actual DTR as inputs. The output of this model are the prediction formulae for defects based on different priority levels, P1 being the highest to P3 being the lowest. To predict DTR, similarity score from test data is an input to the prediction formula. In the next two slides, we will describe two approaches using linear regression to predict DTR. In this approach, we determine correlation between days to resolve and similarity score and derive equations for predicting DTR for different defect priorities. Our research postulates that defects with closely related summaries would take similar days to resolve. We derive correlations between similarity scores and DTR of defect grouped by their priorities using linear regression technique. The idea behind grouping defects based on their priorities is to gain accurate DTR predictions for specific defect priorities. Separate linear equations, as we see here, are generated for defects belonging to P1 stopper, P2 high, and P3 medium defects based on linear fit on defect data. For P1 defects, a positive slope, as can be seen in equation 1 and graph 1, indicates positive correlation between DTR and similarity score. This shows that for P1 stopper defect, as the similarity increases, days to resolve also increase. Thus, similarity of issues does not by itself drive quicker resolution for all P1 stopper defects. However, a low RMSE value of 4.47 indicates that this method can be used for accurate predictions. For P2 and P3 defects, negative slopes in equations 2 and 3 and graphs 2 and 3 indicate that as similarity increases, days to resolve decrease. The similarity of issues does not by itself drive quicker resolution for all P1 stopper defects, whereas it does for P2 high and P3 medium defects. In this approach, we attempt to make our predictions more accurate by doing further statistical analysis on days to resolve using the defects having exactly same similarity score for generating predictions. We group together defects having identical similarity scores. An average of days to resolve for such defects is computed. Supervised learnings based on this average DTR for defects having different priorities P1 stopper, P2 high and P3 medium are then calculated. Predicted DTR for this approach is given in equations 4, 5 and 6. Here also we observe results similar to the previous approach. Positive correlation is seen for the highest priority or P1 stopper defects and negative correlation is seen for P2 high and P3 medium defects. We see a reduction in the RMSE values for P2 and P3 defects compared to our previous approach, indicating this approach results in more accurate predictions. This graph shows the average predicted DTR values against similarity scores ranging from 0.2 lowest to 0.8 highest for priorities P1, P2 and P3. We see that as the similarity between defect increases, the days to resolve a defect decreases for P2 and P3. The key takeaway here is that linear regression and naive Bayes classifier leveraging cosine similarity can effectively predict DTR of a defect. To conclude, open critical defects can cause delay or miss targeted milestones which may negatively impact an organization's interest. Predicting DTR for new defects can assist the developers and project managers to keep their project on track. We saw 3 approaches based on supervised classification and regression machine learning techniques to predict DTR. The output of naive Bayes classifier is either yes if quick resolution is possible or no if quick resolution is not possible in less than equal to 20 days. Considering priority and similarity of defect. Naive Bayes classifier can be used to do preliminary DTR analysis. For detailed analysis, we recommend using linear regression on defect data. Our observations show that similarity score may not be the only factor to predict DTR for all P1 defects, whereas it can be for P2 and P3 defects. This approach can be scaled across different project domains and defect databases. To summarize, similarity score can be seen as a significant factor in predicting DTR for a defect, specifically for P2 high and P3 medium defects. The approaches proposed here can assist the project teams to gain an insight in defect resolution time by helping in quicker defect triage and assigning the defect correctly to keep the project on track. Thank you. We can now answer any questions that you may have.